And let's, sorry, that's a little sideways on there. Whatever, it's just gonna have to be a little sideways. So I don't know how much we want to go into Simpson's rule. Apparently, this is actually a thing that some people like learn in pre-calculus. They learn how to find the area under a parabola using this geometry formula. I most definitely never did that. So if you had a just like fantastic pre-calc teacher that somehow taught you this, awesome. Simpson's rule is coming from this geometry formula for how to find the area under a parabola. Now, we're not usually applying it to parabolas. We know how to find areas of that stuff. But Simpson's rule, just like the midpoint and trapezoid rule, are ways to deal with integrals that we can't otherwise integrate. So I'm going to pick something, and let's go from 1 to 4, 1 over 1 plus x squared dx. By the way, this is one that we could find in our integration tables, but we're not going to do it that way. We are instead going to approximate this integral using Simpson's rule. Oops. Using Simpson's rule with n equal to 6. So let's look at the ugly formula for Simpson's rule as it is written in the book, and then kind of dissect what's going on. So as it's written in the book, we've got that the definite integral from a to b of f of x dx is approximately equal to b minus a over 3n times, and I'm just going to write it the same way it is in the book, f of x naught plus 4 times f of x1 plus 2 times f of x2 plus dot, dot, dot. And we would keep going, and we'd have 4 times f of x sub n minus 1 plus f of x sub n. Now, all that garbage, is really not as terrible as it kind of looks at the start. What happens in here, when we have the trapezoid rule, like, I'll just go back in time for a second to our trapezoid rule. And when we were looking at trapezoids and we had some curve, right, and we were breaking it up, those interior points got used on 2 of the trapezoids, but the outside points only got used for 1 trapezoid. So that's why the coefficients look the way they do for the trapezoid rule. Well, for Simpson's rule, I know it's a little bit weirder to think about, but for Simpson's rule, we're actually breaking this apart. And then fitting parabolas to everything. So because we need 3 points to do any parabola, it just works out that as we're fitting these weird, don't try to draw what I'm drawing. There is a picture in the book of this, but because we're fitting all of these weird parabolas to things, it just works out that this is how the coefficients work in terms of kind of the numbers of parabolas that each one has to get fit to. You don't need to worry about any of that. I'm just like sharing what's going on in the background. In terms of using the formula, 2 things we have to figure out. We need to know what all of our x values are to plug in, and we have to calculate this thing out in front. Sometimes that thing out in front is referred to as h. I don't know why the h, but good times. So let's kind of refocus in on the particular question that I asked. So for the piece out in front, oh, and I said n was 6. So for the piece out in front, this is going to look like 4 minus 1 over 3 times 6. In terms of what goes on the inside, this like 4, 2, 4, 1 thing, the way that that works out, I know that we're breaking up the chunk from 1 to 4 into 6 pieces. So I'm just going to do that. So I'm breaking up 1 to 4 into 6 pieces, which means that must be a 2 and a 3. Decimals or fractions? What do y'all want? Fractions? Cool. So this would be 3 halves, and this would be 5 halves, and this would be 7 halves. So notice if we break that apart, we actually end up with a total of 7 numbers, which is good. So for Simpson's rule, we always have to have an even n so that we end up with an odd set of numbers. And the reason that we need that odd set of numbers is that the pattern for the coefficients kind of works in from the outside in a symmetric way. So these values, the 1, 3 halves, 2, 5 halves, 3, 7 halves, and 4, those are my x0, x1, x2, x3, x4, x5, and x6. Question? Yeah.
So if we're given an n that is an odd number.
Correct. Yeah. So we can only deal with even numbers for Simpson's rule. So I already know that like what's going inside of these parentheses that I probably don't have space for, but I'm going to pretend I do. I'm going to have an f of 1, an f of 3 halves, an f of 2, an f of 5 halves, an f of 3, an f of 7 halves, and an f of 4. The only thing I have to figure out is what the coefficients are that go in front of each piece. So working from the outsides in, we have coefficients of 1, and then coefficients of 4, and then coefficients of 2, and then a coefficient of 4. So the inside ends up alternating. And depending on how many you have, that middle term will either be a 4 or a 2. So I just think it's easier to like work in from the outsides. Now you plug all that stuff in. So just as a reminder, we're approximating this definite integral, which means we are not finding the antiderivative. So when we say we're finding f of 1, we're literally saying that our function is equal to 1 over 1 plus x squared. So like f of 2 is 1 over 1 plus 2 squared. We're not doing the antiderivative. We're just plugging things into this function. And for sure for the homework, pull out that calculator, get numbers into all of that. Questions about Simpsons? It's mostly just a formula. I find it easiest to draw the thing out to come up with the points, but you certainly don't have to do that. That number out in front is not how wide your spacing is. So just be careful about that, right? Because there's that 3 in the denominator. In terms of the formula is division by 3n. The width of each of your pieces is still b minus a over n. No matter which formula you're doing, that's always the width of your pieces is b minus a over n. Yeah.
Dumb question.
It's probably not.
Is B, is that thing of B minus A divided by N also equal to B minus A over N over 2?
Sure. You could also write it as 1/3 of B minus A over N. I just went with, this is how the formula is written in the textbook. So I just went for that version. Okay. I'm going to move on to old stuff, meaning reviewing limits. But there's a question in the chat that I've also been getting a lot on email. So I did want to address that, which is, where are the recordings that I'm making going? So in Canvas, in my Canvas, not the Canvas for your 16B class. So if you're not in my Canvas, for sure, let me know. You can always put your email in the chat, or let me know if you happen to be sitting in the room right now. Of course, now I can't get Canvas to load, so I'm just going to pretend that I have Canvas up. But if you look in the modules in Canvas, there are, my modules aren't necessarily given like by dates, they're given by topics. But if you look in the modules for the topics, that's where the notes and corresponding videos are. And I think I'm caught up on video posting. So I also have way more videos than that on my YouTube channel. So I often, if I know that I have another video that I've recorded previously on a similar topic, I'll usually add that in the end screen for the YouTube recording from this class. So, yeah. Okay, good times. Fast forward to limits, or rewind to limit stuff. I don't know how much everybody remembers about limits. I'm gonna pretend that it's maybe not a lot and that I'm gonna dial it like way back, but I can hit the fast forward button if I need to. So there are some limits that are going to be important for us in this next section. I happen to like pictures. So I am going to draw a couple pictures and then we're going to explore some limits based on the pictures that I've drawn. So that's going to be x equal to 1. That's going to be y equal to -2. And I'm not actually going to tell you what the function is, but using the graph, see if you can come up with values for these limits. So I want the limit as x approaches 1 from the left, and the limit as x approaches -infinity, and the limit as x approaches +infinity. It'll probably take you longer to draw the picture than to evaluate the limits. Sorry? Oh, this is all one function. This is one graph of one function. But I will say that notation wise, having this vertical dashed line means there's an asymptote there. So we are supposed to assume that there's an asymptote there. Okay, so let's take a look at what these limits are doing then. So notation wise, I would read this as the limit as x approaches 1 from the left. That means that I start on the left-hand side of 1 and move towards an x value of 1. The answer to a limit problem is always what the y value is trying to be. So as I'm coming from the left, this y value is headed to positive infinity. Now, if I'm looking for the limit as x approaches negative infinity, that's saying that way out on the left-hand side of the graph, what's the y value that the curve is approaching? Yeah. And on the right-hand side, my y value is approaching the same thing. That's also headed to -2. Now, I find that in general, if I give you the graph, people are pretty good with limits. But now I'm going to not give us the graph because that's more realistic for most of the problems that we're going to see. So if I wanted to take a look at the limit as x approaches 2 from the right, and my function is 1 over x minus 2 cubed. Thinking back to what we would have done in 16a, the first thing that we would try with any limit problem is to just plug the value in. But when I plug 2 in, I end up with 1 divided by 0 cubed. Well, 1 over 0 is an indeterminate form, but back in 16a, we know something about this limit. 1 over 0 cubed is either headed to positive infinity or negative infinity. And it's our job generally to figure out which. Does anyone want me to show why this is headed to positive or negative infinity? I don't know how we feel about our 16a stuff. Yeah? Okay, so let's talk about why that's headed to plus or minus infinity. And again, it's one or the other. I don't mean to imply that it's both. Two things. One, I know that based on this graph, I have a vertical asymptote at 2, right? Like that's a thing that I know. But just numerically thinking about what's going on here, what's happening with the limit is we're getting really, really close to that number. So if I pick a number that's close to 2, but a little bit bigger than 2, I don't know why I cubed this. This is going to be gross. It's okay. I can do this. I can handle the math. Okay. I'm going to pick something really close to 2, but not so close that I can't do the math. I'm going to go with 2.1. So 2.1 minus 2, that means I've really got like 0.1 and it's being cubed. But my brain doesn't work so well with decimals. So I'm going to change that decimal to its fraction form of 1/10, which means that's the same as 1 over 1 cubed is 1, 10 cubed is 1,000, right? Yes. And 1 divided by that makes it flip over, meaning that is equal to 1,000. So I started off pretty close to 2, not like crazy close, but pretty close to 2. And if we work the math out, that 1 divided by a small number is actually a really big number. So if I get even closer to 2, like 2.01 minus 2 cubed, I'm going to kind of hit the fast forward button on here. That should be 0.01 cubed, which is like 1 over 100. Dang, that's a lot of zeros. I'm going to be lazy. I'm going to call that 1 over 100 cubed, which is like 100 cubed, which is big. So the closer that I get to 0 in the denominator, the larger the overall thing becomes. What we need to know, just like for the context of 16b, is if we're doing a limit and you get a number over 0, that's either headed to positive or negative infinity. It doesn't matter what the number is. All that's going to change is whether it's going to positive infinity or negative infinity. So for this particular one, how would I figure it out? Well, if I'm a little bit bigger than 2, then the bottom's going to be positive. So I'll have like 1 over a 0, but it's a slightly positive 0. Other important limits. This is just kind of like basic fun with limit stuff. So if I look at the limit as x approaches infinity of 5 over x squared, well, the first thing that we try with any limit problem is to plug it in. But if I plug it in, that's going to look like 5 over infinity squared. And I think we maybe kind of talked through this last week, something similar to this. But if I had $5 and I tried to share it with everyone on the planet, nobody gets any money. Because 5 divided by infinity is going to 0. So a number divided by infinity is headed to 0. And these two kind of limit facts, they're going to be important and they're going to come up over and over again. By the way, this is true no matter how big the number on top is, and it's true no matter kind of how big the power of x is on the bottom. But things to be careful of. If I looked at the limit as x approaches infinity of -3 over x to the -2, I probably want to simplify this a little bit first before I try to take the limit. Because if I just think about plugging that infinity into the bottom, I'm going to have infinity to the -2 power in the denominator. But this whole thing, I can rewrite to look like -3x squared. That is definitely headed to negative infinity. So it will be useful to be able to recognize like when to move exponent stuff around. Similarly, if this whole thing were flipped over and I was looking at the limit as x approaches infinity of x to the -2 divided by -3, before I take the limit, I really want to rewrite that to say the limit as x approaches infinity of 1 over -3x squared. Now I'm in that realm of when I go to plug in the infinity, I've got 1 divided by a huge number. This thing's going to 0. I have 6 more limits for us. And then we can do some calculus with them. Those 6 limits, you could choose to just memorize, you could choose to write a picture for them, but there's 6 limits involving natural log and e. And, oh, maybe it's 8, I don't know, 6 or 8 limits, we'll survive. So I'm going to draw 2 pictures again, because that's how I think about all the limits. So here is y equals e to the x. And it's important to know that that intercept is at 0, 1. So from the graph, we should be able to evaluate the limit as x approaches positive infinity of e to the x. The limit as x approaches negative infinity of e to the x. The limit as x approaches 0 of e to the x. All of those show up fairly often in our improper integrals section. How are we doing? Got answers of all of them? What's the limit as x approaches positive infinity for e to the x? Totally. How about the limit as x approaches negative infinity for e to the x? And the limit as x approaches 0 of e to the x is 1. Now this middle one takes a couple forms because that middle one is equivalent to saying, what's the limit as x approaches positive infinity of e to the negative x? So these are secretly the same question. And both forms of that will definitely show up when we're doing improper integrals. Now e is, I don't know, cousin ln of x. I don't actually know what. So if that's y equals ln of x, this intercept is 1, 0. And we can ask similar questions. We can look at the limit as x approaches positive infinity of natural log of x. We can look at the limit as x approaches 0 from the right of ln of x. And we can look at the limit as x approaches 1 of natural log of x. What we can't do is look at the limit as x approaches negative infinity for ln of x. Thinking about the graph, it just doesn't even exist over there on the left-hand side. So as x approaches infinity, ln of infinity is headed to positive infinity. This thing is just keeps going up. As x approaches 0 from the right, natural log of x goes towards negative infinity. Because this is headed down. So we're thinking about what's the y value we're getting close to. And natural log of 1 is 0. These are all limits that you're going to want to be like comfortable and familiar with for doing this next section. So I choose to just like in my head, think about what these two graphs look like to answer all the limits. If graphically isn't working out for you, it's not that long of a list. You can make flashcards. Y'all made flashcards to get through all the trig integrals. So you can do the same thing here. Should we apply it to some calculus stuff? So we got a little start on this last week, but I know not everybody was with us on Wednesday. So as kind of a quick recap, what's happening with improper integrals is one of two things. So the other day we looked at a couple of functions, and one of those functions that I gave us was y equals 1 over x squared. Well, so far when we've been finding areas, we've always had like finite endpoints, right? Maybe we're integrating from 1 to 4 or something and looking for the area in here. Well, the idea behind improper integrals is that they're unbounded. So rather than stopping there at 4, we actually found the area if we kept this going forever. Now, not that much changes about the mechanics of what you do. We just add on a little bit of additional notation. So the notation comes in with, we only know how to write a definite integral, kind of if there's a wall there. So we're going to put in a wall, and I'm just going to call it B. So if I write an integral to represent this area in here, that definite integral would say I'm going from 1 to b, and then I'd have my function 1 over x squared dx. The only extra thing that we're putting on this to make it unbounded, so we're sticking a limit out in front so that b approaches infinity. Next 2 steps are the same as they are with any definite integral. We find that antiderivative, we plug in the endpoints. So if I find that antiderivative, I didn't leave myself a lot of space here, but if I find that antiderivative, I'm really going to think about 1 over x squared as saying x to the negative 2. So I would add 1 to the exponent to get x to the negative 1, and then divide by the new exponent. So there's my antiderivative piece. And then we're evaluating that from 1 to b. But I mentioned before that if we're going to do limits, it's nice to not have negative exponents. So I'm going to rewrite that to say 1 over negative x from 1 to b. So that I can plug in my top 1 over negative b minus 1 over negative 1. Now we're ready to take the limit. As b approaches infinity, 1 divided by b is headed to 0. Here I've got minus a minus, so that's a plus 1. I'm pausing there in case there were questions. I wrote a lot of stuff. I'm not seeing questions in the chat. Should we just get another example going? Okay. So there are 2 kinds of improper integrals. Integrals can be improper because the bounds are infinite, right? In this case, really, I didn't have a bound. I wanted to be headed to infinity. So I can have things that look like we're going from, 1 to infinity or negative infinity to a number. These are things that would make my integral improper. But we can also have an improper integral happen because we have a vertical asymptote. So the other way improper integrals happen is if I had something that looked like, I'm going to go back to something we had before, kind of, I don't remember exactly what I wrote, so I'm just going to make it up. Let's say I had 1 over x minus 2 cubed. And I wanted to integrate from 2 to 4. This integral is improper because I don't know what I wrote. Whatever, sure, because there's a vertical asymptote at x equals 2. So this bound of 2, it is not itself infinity, but it is a place where there's a vertical asymptote. So there's a kind of infinite thing happening there. If I were to sketch this out, it kind of looks like this, which means the area we're finding, yeah, no, it doesn't. It does now. The area we're finding is from 2 to 4. So this area is not bounded because it's heading up towards that vertical asymptote. So to set this up as something that we can work with, we're going to build ourselves a wall. So I'm going to build myself a wall here at A, and I'm going to write my integral going from A to 4. I'm going to take a moment to write this integral as x minus 1 to x minus 2 to the negative 3, just because I know it's going to be easier to integrate looking like that. But in terms of the improper integral, I built myself a wall at A, and then I'm going to take this limit to push A towards 2. It doesn't always matter, but sometimes it does to know whether we're coming from the left or the right. So mathematically, we do want to either put a plus or a minus on it when we're dealing with a number. So if I think about all the numbers between 2 and 4, they're all on the right-hand side of 2. So that's how I know to put the 2 over there. I mean, to put the plus there. Because all the numbers between 2 and 4 are on the right-hand side. Now we integrate it, plug in the endpoints, and evaluate the limit. I'm going to give you all like 2 minutes to do that. So find the antiderivative, plug in the endpoints. Evaluate the limit, 3 steps. Should we find the antiderivative together? So if I integrate this, I'm going to end up with x minus 2 to the negative 2 over negative 2. And we're going from A to 4, and we've still got that limit as x approaches, as A approaches 2 from the right. I'm going to choose to rewrite this so that I don't have negative exponents anymore. So I'm going to choose to write this as 1 over negative 2 times x minus 2 squared before I plug in my a and my 4. Don't have to, just it helps me in terms of figuring out the limits. Kind of like in 21A, you might have someone who's picky about writing the limit on each step until you take it. So just remember to do that. If we plug in 4, that's going to be negative 2, and then 2 minus 2 is 2 squared minus 1 over negative 2 times a minus 2 squared. Now we're ready to evaluate the limit. There's nowhere to plug the 2 into the first part, so we're done. Like that piece just is what it is. That looks like negative 1/8. Minus a minus, so I could write that as a plus. Here, if I plug in 2, 2 minus 2 is 0. I have a number divided by 0. I know we're headed to either positive or negative infinity. Since we're squaring the thing, I know for sure we're headed to positive infinity. Now, when we have evaluated one of these definite integrals and we get an infinity in the end, we say that it diverges. So a lot of times the instructions in the book in this section will say to evaluate or show that it diverges. I think we have time for one more example. Should we do one more example? Let's do one with e's in it. Sliding this up a little. So let's find the integral from negative infinity to 1 of, oh, how bad should I make it? Do you want it to be messy? Moderately messy? Moderately messy. Okay. Let's go with e to the x over 2 plus e to the x dx. First step is the mathy notation part. This is an improper integral because we have an infinite bound. So we have to do this thing where we force it to have a bounded side. So we're going to switch this around to say the limit, and you can pick a letter. I'm picking A, goes to negative infinity, and we're going to go from A to 1. Next step is we have to actually evaluate this thing. So if I walk up to this integral, I've got e to the x stuff in there. I'm hoping for a u substitution. And luckily I gave it to us. I'm going to make u equal 2 plus e to the x, which means my du is e to the x dx. And I've already got that sitting there on top for me. So I've got a limit as a approaches negative infinity. And I'm just going to remind myself that I'm going from x equals a to x equals 1 because I'm writing out that u sub of 1 over u du. Now I'm going to integrate this thing. She's so afraid of calculus. So if I integrate a approaching to negative infinity, when I do this integral of 1 over u du, we all know and love that natural log. I'm going to go ahead and just skip to the step where I write that as ln of 2 plus e to the x. And we're going from A to 1. Now, we don't have to worry about absolute value here. 2 is always positive. E to the x is always positive. We're good. We know the stuff inside is positive. Just 2 more steps. I'm going to plug in those endpoints. So I'm going to end up with ln of 2 plus e minus ln of 2 plus e to the a. Sorry, it's getting kind of low. And that's an e because e raised to the first power. We can just leave as e. And now when I evaluate this limit, there's nowhere to plug it into the first part. So the first part is just going to be ln of 2 plus e. Nothing we can do with that. But over here, I'm going to have e to the negative infinity, which is going to 0. So I've got ln of 2 plus e minus ln of 2 plus 0. I don't know what it is, but it's a number. So I'm calling us done. I'm not sure I have time to finish another example, so I think I'm gonna leave it there. I do have Zoom office hours from 2 to 3 today. If anybody wants to, yeah, there's a question in the chat. Yes, we could call this convergent because we did not get infinity. We got a number. We say that it converges. And with that, I hope you all have a lovely rest of your day. If I don't see you from 2 to 3, I've got office hours tomorrow morning, 9 to 10 over in C class. And that's all.